you're going to use the property of inverse derivatives. Let's see, 29C, let f of x equal cosine x plus 3x. Oops. And the question says, show that f has a differentiable inverse. Find the inverse at 1 and the derivative of the inverse at 1. So let's remember something here, and this is agreed? Reflection across y equals x is an inverse function. So if I look at this point, and I'm going to call this A comma B, there is a derivative f prime of A, agreed? And I can calculate that. Slope, of course. Now, let's think about the derivative of the inverse function, not drawn to scale, by the way. The derivative of the inverse function, f inverse prime, at, well, if, let's put that point there. If this is A comma B, do we agree that that point right there on the inverse is B comma A? So this would be the derivative of the inverse at B, and that's the derivative of the function at A. So I've got two slopes. I've got the slope of the original function at A comma B, and I've got the slope of the inverse at B comma A. And this is all just principles of inverse. Inverse is a reflection across y equals x, which means every point switches. AB becomes BA. Turns out there's a relationship between those two numbers. The derivative of the inverse at B is equal to 1 over the derivative of the function at A, and vice versa. The derivative of the function at A equals 1 over the derivative of the inverse at B. So when you're looking at a problem like this, the question is, first off, what are my points? I need to know A and B. Because when I know A and B, I will also know B and A. So when I look at this problem, they ask me to find f of 0 and f prime of 0. So that means that we can assume that A is 0. Agreed? So what's B? Well, cosine of 0 is 1, plus 3 times 0 is 1, which means that B is equal to 1. So I now know my point. F prime of 0 must be equal to 1 over F inverse prime of 1. Agreed? I don't want to switch those. And probably more usefully, the derivative of the inverse at x equals 1 is 1 over the derivative of the original function at x equals 0. And the reason I say more usefully, because I can find the derivative of this. F prime is equal to, well, whatever the derivative of that is. And then I can plug in 0, and then the derivative of the inverse function must just be 1 over whatever I get. Now, how do I prove that the derivative exists? Well, does this derivative, let's generalize this a little bit more, Hang on just a second. So I'm going to go back just a step to, well, actually, I'm going to go back just a step to here. If I need to prove that this exists, what must be true of that?
Also has to exist.
Has to exist and
Not zero.
can't be equal to zero. There's the important point. If this derivative exists, which, yes, it does, it's a differentiable function. If it's ever equal to zero, then there are places where this derivative doesn't exist. So if you read that question carefully, it says prove that it is differentiable for all values of x. If this is ever equal to zero, then that's not differentiable for all values of x. Let me double check what the question's actually asking. Show that f has a differentiable inverse. Actually, so we're not even concerned of differentiable. There could be places, it could still be differentiable in places. So when we're talking about that, there could actually be places where it's not always differentiable. But, so what's the derivative of cosine? Negative sine. What's the derivative of 3x?
3.
So the derivative of the inverse is 1 over negative sine, let's say at b, a plus 3. Does that ever equal to 0? So that would be equal to 0 when negative sine a is equal to, or plus, excuse me, plus 3 is equal to 0, agreed? Which means that this is that sine of a is equal to 3. Could you guys list all of the places on the graph of sine where it's equal to 3? You can't, or there aren't any? Why not?
Because it never equals 3.
Yeah. Sine cycles between. In fact, this can never equal 0, which means that this function is differentiable for all values of x. And so this is an interesting question, though. When they say a differentiable inverse, there's a couple possible ways to answer that. You could say a function is differentiable on this interval, or you could say it is just differentiable, which means everywhere. And so if they say show that it's differentiable, I would say that they probably mean show that it's differentiable everywhere, because otherwise they'd say show that it's differentiable on in this interval. So just the plain old, is it differentiable everywhere in the domain? And since the domain of cosine is infinite, then that means that we're looking to prove that it's differentiable infinitely. That makes sense? This is this is a complicated concept. When I started teaching calculus, I hadn't thought about this in a very, very long time. Man, it took me a while to wrap my head around it, because there's so many little marks. There's the inverse marks. There's the derivative marks. There's the A's and the B's, which are switching back and forth. And I think really the way to think about this problem really is visualize two functions that are inverses of each other, visualize A and B, recognize that therefore the other one has a B and an A, and then go to this. So you have to do two things. You have to take the reciprocal of the original derivative, and you have to switch the points. If you think about those two things, reciprocal of derivative, and part two, switch A and B. Do those two things, this becomes a much easier problem if you think of it that way. Cool?